Here is a example. It's an exercise to use the mechanical energy concept for a flowing fluid to estimate the potential of generating electricity or electric power from a reservoir, a water reservoir. Okay, here this is a reservoir that's with that has a water level elevation difference of 160 meters. So let's see how we can determine the power generation potential of this control volume of this situation. Let's see. So I have drew a schematic of the reservoir. This is the reservoir, and there's water inside. And this is point 1. This is the highest point that's the free surface of the top of the reservoir, and this is point 2. This is the lower point where the water would exit from the reservoir after doing work to drive a turbine and generate electricity. The elevation difference between these two points is 160 meters. Okay, so we use the concept of flowing fluid mechanical energy. This is especially convenient because water is an incompressible fluid. The density of water barely changes. If it changes, the change is very, very small. It's not negligible. So we consider this water to be incompressible fluid. And the mechanical energy at point 1 would be expressed in such a way. And then the mechanical energy at point 2 is this expression. Now we want to see how much the mechanical energy changes for the water, the flowing fluid. And if we know the mass flow rate of the flowing water, we can multiply the change in the delta E by the mass flow rate, and we can get the potential to produce electric power based on that rate of energy change between these 2 points. Okay, so it's easy to see delta E. I'm using the absolute value of delta E just to make things simpler. And you should know that the mechanical energy of water actually decreases from point 1 to point 2 due to the elevation difference. So this pressure difference, this term should be negligible, should be 0, because the pressure at this point is P1, and this point at 2 is P2, and there's a open water surface at this point too. So there is slight change in the pressure of water, but the pressure of water, the water is exposed to atmosphere at point 1. The water again is exposed to atmosphere at point 2. So the change would be equal to the atmospheric pressure change between 1 and 2. As we know, air is a very light fluid. The barometric pressure difference between these 2 points will be very small. You can actually calculate how much that is using the density of air, roughly 1.2 kilogram per cubic meter. You can do the calculation. So this is almost 0. And if we assume the velocity of a water flow is the same, or is almost the same between 1 and 2, this term also becomes 0. So the only term that's significant is this term. That's due to the elevation change. So the only significant change in the 3 components of the mechanical energy is the potential energy change. And then we can substitute that delta E into this expression. This is the difference in the rate of mechanical energy flow between point 1 and point 2. And you can do the calculation. This is roughly, if my result shows 5.5 or 5.49 megawatt. Okay. So this, technically speaking, is the mechanical energy, is the difference in mechanical energy rate of mechanical energy flow between point 1 and point 2. And the reason that mechanical energy flow rate would change is because that mechanical energy has been converted to something else. The most useful conversion would be to convert that mechanical energy of the flowing water to electrical energy, to electrical power. And certainly there's a question of a conversion efficiency. Now, if you have a conversion efficiency of 100%, then you can assume that the maximum, the power generation potential for this reservoir is 5.5 megawatt. And certainly, it's only when we have learned the energy balance, energy conservation principle for control volume, and also the energy conversion efficiency concept, that we can properly solve this problem. But here, knowing that the mechanical energy change, or the difference in rate of mechanical energy flow between point 1 and point 2 should be sufficient to allow us to solve this problem in a preliminary manner.